Okay, so I wasn't sure where we ended last time, so we're just going to start here, and I'm going to repeat a few slides. So you can always advance. If you were watching the recording, you can just kind of skip through these slides. Isn't that the great thing about recording? Just some updates. First of all, Friday we are live, so you will be on the Zoom on Friday. I don't do Zoom Monday and Wednesdays because it's too hard for me to do all the technology. So we will be live on Friday. I will give a homework assignment. It's really simple. It's going to be on looking for journals, and I'm going to go over how do you do look for journals articles. So that'll be on Friday. We will go over that, and I'll answer any questions. We're going to be moving on in the next. So you had a homework assignment due. Hopefully everybody turned that in. If you did not get it in, email it to me. Did you get your homework assignment in?
Yep.
Awesome. It probably wasn't that hard. No, but it gets you thinking, and so I'm going to look at that. In the book here, we're going to be doing chapter 7. As soon as I finish this lecture, we're going to be doing organic compounds. There isn't a homework assignment for today because we haven't started organics, but as we move into organics, either Wednesday or next week, Monday, you'll get a homework assignment. So just keep that in mind. But if you want to catch up with the readings, we're in chapter 7 of the book. Okay. What we've been talking about is groundwater contamination is usually difficult. One of the reasons that groundwater, I think I know I talked about this a little bit, is just detection. You could have a pollution, and if it hasn't gotten to a well yet, you might not even know it's there because it's so point source. With wells, it's very point source. And so you don't know if you're going to hit it or not. You can't put in enough wells in order to be able to see all groundwater. And this even goes into when you're doing geologic mapping using well logs, because you're going to be doing that for part of the class at the end of the class. I'm going to have you guys, I don't know, do you know Illwater? Okay, I'm going to introduce you to that because it's really important, even though you're doing stuff in Alaska. Tony's here, so you guys who are watching online, you guys know what's going on. So this is going to be very happy, live here. Even though you're doing stuff in Alaska, it's good for you to know in the state of Illinois resources that we have for water. And so we're going to go into some of those. And I'll have you guys do an assignment with Illwater and some water quality analysis that's in the state of Illinois, because we're going to do a little project near the end of the class on water contamination in the state of Illinois. If we could go out to the field, I would show you guys how to do field work too, but that's not going to happen right now. But it's very hard to get it, and until a water supply is affected, usually people don't even know that there's contamination going on until there is a water supply, and even then, people may not even know. Things like MTBE have like a taste of turpentine at very low levels, so you smell and taste it. But like lead does not have a smell or taste, and so we're going to talk about the lead, and we're going to talk about social justice and systemic racism associated with Flint when we get to the lead section of this class, even though that's not a groundwater contamination issue. So it is totally a structural thing, but we're still going to talk about it because I like talking about Flint. I think it's interesting. But if you can't taste it or smell it, or and then sometimes cancers, we'll talk about the civil action. Cancers don't come up until maybe years later, or you notice, oh, your neighbor's also having a miscarriage, and I had a miscarriage. These things don't happen very effectively. So groundwater sometimes is really hard to detect. The other part of it is, like, if you're in rural areas, you don't have to test. So you never even know if you have a problem. Next slide. So it's particularly unsuccessful. Again, the contaminants can get trapped inside of low K zones. So like clays act as like little sponges, and they'll get stuck there. So one of the first pump and treats that they ever did. So pump and treat is the number 2 way that we clean up contamination. So the number 1 thing we do when we have remediation of a contaminated site is we dig it up. We dig up the source, we dig up the soils. Number 2 is pump and treat. Well, the first case that they did with that, they started doing pump and treat, and within a year, they couldn't even detect the TCE in the water. Then all of a sudden, they turned off the wells, and they came back 6 months later, and they turned them back on, and the concentration in the wells was back up to the exact concentration it was before. And they're like, but we pumped it all out. What happened? And then they realized that there was a low K zone, and it was just, they flushed it so fast, they got all the water through it, the groundwater through the site, but they did not take into account that these low K areas were just like oozing the contaminants out for long periods of time. So that was one of the first pump and treats, and that was done in the 80s, and that's when they realized that contaminant hydro was a lot harder than we originally thought. And the thing is most sites are only characterized, again, by one well. Like, we might put in a well, and then us as geologists have to come up with this whole idea of what this whole site looks like. And if you're in Illinois, where we have glacial materials where it might look flat, but it's really complicated geologically, you don't know where the stuff is happening. So it's often hard to remove the source contamination. And then there's also, I mentioned before, unrealistic expectations. Large zones for unpredictability. It depends on the site's geology. That's why contaminant hydrogeologists are, I think the better ones are if they're in geology, but they also come out of civil engineers. So a lot of times civil engineers, when we go to groundwater meetings, half the people are civil environmental engineers and the other half are geologists. The problem with civil engineering is they never have to take a geology class or any sort of earth science class. So I'm trying to change that. We're starting a new degree here in environmental engineering, and I forced them all to take geology classes because I was on the curriculum committee. I'm like, they all need basic geology and more. Oh, and then we had a big debate with them because they were going to offer an environmental or engineering geology class, the tech class that Phil offers. They were going to offer the exact same class with the exact same book. And they're like, oh, no, but these are engineers. They have higher levels of math. And we're like, it's the same book. Yeah, it's only you guys watching these videos. Groundwater moves extremely slow, and I mentioned that last time. I talked about the wells and the family in one project I was working on where it really took them a long time for it to get flushed through. Groundwater moves extremely slow, and I don't think people realize that. And so people think that, you turn on your water today, it's what happened. Groundwater moves extremely slow, and it takes a long time, unless you're like in a karst system. It moves extremely slow. And then small heterogeneities. So one of the first sites that they started doing this type of work was at the Borden site. Now I know I'll be talking about the Borden site because that's where I did my master's up in Canada. And they could do where they pinned hole, like they had a well site the size of our classroom here, and they had taken a core every meter in the thing, and then they mapped it down to, and could see all the small heterogeneities when the site looked like it was just sand. It was just an outwash sand. And that's all they thought it was until they mapped it at that scale. And so that little bit can change totally how you're modeling. That's why when Megan does the modeling, I'm like, good for her. It's so complicated. I'm like, it may show up somewhere within the next couple of years. That's as much as I can get into it. Okay. So the discovery stage, the study of contaminant hydrogeology is still at the discovery stages. So back in the early 80s is when we started looking at NAPLs. Now, you guys see the word NAPL on there. What does NAPL stand for? Do you know what NAPL stands for? NAPL stands for non-aqueous phase liquids. So non-aqueous phase liquids. This is probably, I'm going to pause for a second. Some of my things, I'm not super formal. Okay. So NAPL stands for non-aqueous phase liquids. So that term was coined in the 1980s when we started looking at different types of contaminants that were non-aqueous phase. So what are examples of non-aqueous phase? And we're going to be spending a lot of time with them for the next couple of weeks. So by the end of September, you're going to be like a whiz at these things. But NAPLs stand for this gasoline, anything that doesn't mix with water. Oil and water don't mix, right? Well, they do, and we're going to talk about that. That's going to be after we get through the first part of the organics and we start getting into some of the properties of it. We're going to start talking about how it actually is soluble. So something like trichloroethylene, or TCE, is soluble at 1,500 milligrams per liter, but the MCL for it is only 5 ppb. So I just said a whole bunch of words in there. MCL. Do you guys know what MCL stands for? There we go. Good. Maximum contaminant level. So MCL is a really good one for you guys to know. MCL. Maximum contaminant level. TCE, trichloroethylene. That's the Civil Action book. So you guys will know that one by the end of this. What's the difference between I'm going to switch my camera here. I think I'm going to try. I don't know if I can. While I'm recording. But what's the difference between ppb and micrograms per liter? I'm going to stop. But what's the difference between ppb, ppm? Do you know what those stand for? And one's parts per billion, one's parts per million. What's another way of writing ppb? Micrograms per liter, and ppm is milligrams per liter. You should know those. I'll write those up on the board for you. You can't see I can't project. ppm equals milligrams per liter, and ppb equals micrograms per liter. Okay, so TCE, which stands for trichloroethylene, we'll spend a lot more time talking about that one, is soluble at 1500 ppb, but its MCL is 5 ppb, or 5 micrograms per liter. Okay, so so for you guys who are online, TCE, its solubility is 1500 ppb, but it's MCL. So what that means is that when you have something like a DNAPL or a NAPL, we're talking about NAPLs here. When we're talking about NAPLs, if even though it says it's insoluble because it's a phase liquid, it's a non-aqueous phase liquid, they don't mix, it's still slightly soluble, even if it's just a little bit soluble, but it's so much higher than the MCL that even if it's just slightly soluble, it's in there. We'll also talk about the BTEX compounds in a little bit. Okay, let me switch my... So with this, the conceptual models here, what we have here is the upper corner here. So if you have a DNAPL, which stands for dense non-aqueous phase liquid, so that's your TCE. So when I say dense, I mean they're denser than water. So what happens when you mix it with water is it sinks to the bottom, and then it hits and it pools onto an impervious aquitard or a slate or a clay. And so it'll keep moving down through it. And as the groundwater is moving through this oozing part that comes down in here, what happens is that you can see the contaminant just dissolves as it's coming through there. So this acts as a horrible thing. So if you have a contamination between a BTEX compound or a TCE or your DNAPLs are much worse because of like that picture that I'm just showing you right there, is that it just keeps going down and then it pools at the bottom of your aquifer and then acts as a large source of it. It gets trapped in these little pores between the grains that just slowly dissolve with time. The other thing that's very common, it's your picture on your right here, that happens really commonly too, especially around here, is you can get a clay lens, but we have a lot of fractures in our clay. And so the DNAPL won't stop. It'll just find these fractures and it'll keep going down to lower and lower aquifers too. And then go them. You can actually get DNAPLs, and you see here, because this is another misconception, it's like, well, if I'm up gradient, how can I have the contaminant up gradient from where you are? Well, DNAPLs are actually more influenced by gravity, especially the pools of them. So these pools at the bottom of that screen on the far right, it shows it going upstream because if there's a slight angle to the ground there, it's going to go the direction, it's just going to go by gravity. It's not going by groundwater flow. So you can actually get him up gradient and moving up gradient. So it's fun. It's... Yes, yeah. And then also DNAPLs are less viscous than water. So they have a low viscosity. And we'll talk a lot about those. We're going to be getting into like all the properties of all of them and then doing some calculations based upon these things. But I have to introduce you to the words and the concepts before I start getting into like all the math. It's in there. Okay. The other thing that happens, and this is something really important for Alyssa, so Alyssa should be paying attention here, is colloidal facilitated transport. So colloids are anything that are small, like fog is considered a colloid. So it's anything that's a small particle size. What they were finding too is that colloids could be transported through the environment, and so we're looking at microplastics right now. So one of the you're going to be reading a lot on microplastics this semester, I suspect, or at least some papers on microplastics. But colloids can actually act as a way of transporting contaminants. So we can get clays or iron oxides that move through the environment, and you can get sorption. So, okay, here's another fun word. I'm going to stop. Okay, so let's see, is it recording? Yes. So, sorption is the term that we use a lot. So what happens is this is a combination of two terms, absorption and adsorption. So what's the difference between these? Well, absorption is where we absorb something, so like a sponge. So this would be sponge-like. Adsorption is more like a magnet. It sticks to the outside of it, okay? So what happened is we kind of go, well, we really in contaminant hydro could care less if it's stuck to it or absorbed into it, because we really just don't care about those terms. So we just use the word sorption to mean both processes, because on a physical process, these mean exactly the same thing. So we use the word sorption. So colloids, we're doing a lot of sorption, and what would happen is these things would move. So these iron oxides that you see here on the screen, these clays and stuff like that, they would move, and then you would get sorption of, say, like radionucleotides to them. They would stick to it, contaminants could stick to them, and then these colloids could actually move and carry contaminants to other locations. The other thing that colloids can do is when you look at something like this with the fracture flow, colloids, because they find the least resistance, as you mentioned before, the path of least resistance, what ends up happening is colloids can actually move faster than the groundwater, because they will find the absolute fastest way to go, and you can actually get them going faster. So sometimes you can get colloidal transport being some of the worst kind of problems that can happen with that. And so the EPA banned the process of filtering groundwater because they, started to process, ban. So they started to propose a ban on filtering groundwater samples for testing, because what happened was when you're trying to test for contaminants, if you filter out all the colloids, you might filter out all the contaminants. So when you're looking for stuff like radionucleotides, you're looking for any of those kind of things, you want to keep the colloids in the sample. So what they wanted to do is allow some samples to be filtered, some samples not to be filtered, because you may lose out on the process. But the problem is if you don't filter the samples, like if you guys are using the IC upstairs, the IC or the ICP-MS, do you guys know what those stand for? So IC is ion chromatograph, and then this one is inductively coupled plasma mass spectrometer. So this one does heavy metals. And then this one does your major ions. So the IC, we usually filter before them because the equipment is so expensive. Like this thing is like $500,000 and stuff like that, that you don't want dirt stuck into it, or you don't want these colloids to get trapped in there. But the thing is that's where the heavy metals would be. So a lot of environmental laboratories have two sets of equipment, one that are for colloidal testing to see if they have things like heavy metals onto it, and then other ones are for the more dissolved ions inside of it. Okay. So the next other major problems are poor coordination between many disciplines involved with groundwater contamination. As I was mentioning earlier about the environmental engineers and stuff like that, never taking a geology class, well, they were making decisions because they're an engineer and they have a little PE after their name. They could sign off on things that we couldn't even sign off on. And they didn't actually understand the geology, the physical flow and stuff like that. So again, we're trying to do more cross-disciplinary. That's why we have interdisciplinary centers now. When I was doing my PhD, I was one of the first people trying to work on this idea of doing microbiology and hydrogeology together. And, you would have thought these things would have been talking for years, but they didn't. So a lot of disciplines don't talk to each other, but we're doing a better job of that now. This is why it's good for you to take classes outside of one discipline. There's a public demand has forced application of clean up and technologies before the basic principles are well understood. Like if somebody comes up with a new idea for cleaning up a site, people are like, hey, let's try it out. And then you're like, well, I don't know if this is going to work or not, you know, and so sometimes people like the new technologies better than, or trying something new that's, you know, someone sells for them. There is a shortage of well-trained professionals in key decision-making processes. So what happened in the contaminant field was the 1980s, there was the oil bust. So everybody went into the environmental field. So they were all oil and gas guys who went into the environmental field. They learned it kind of on the field, but now they're all retiring. So there's a lot of jobs in contaminant hydro and in the hydro field right now because they're all retiring. We have younger and older, and we need people in key things that are actually were in that middle range of ages. So that's another problem, and so we really do need more people in this field. And it's difficult to distinguish between effective and ineffective characterization, remediation, and contamination efforts. So what can happen is you can, and I've done this because like I told you before, I do expert witness. And I mean, I know the guys who are against me on these expert witness, and we come to totally different conclusions and stuff. Because a lot of it, there's that one, I should put that one cartoon where, you know, geology is just a lot of, you know, whiskey and dreaming and stuff. You know, there's a lot of interpretation when we come to geology, and groundwater is no different with it. And so we can get different interpretations based upon the exact same data set, which is totally normal. Geology and groundwater contamination. Geologists are particularly well suited. That's why I think that you should all have to take a groundwater class. And then I'm going more into the pollution side of things. So the combination between a hydro class and this is great for all geologists to have. Because a lot of times, especially if you're going to get a job in the Chicagoland area, this is what you're going to do. The physical and chemical properties of subsurface materials, which influence groundwater flow and natural water chemistries, are a direct result of the geologic environment. So when we start looking at things like arsenic, we're going to talk about arsenic, we're going to talk about fluoride. You have to know what the geology is of the area. And so one time there was a history professor. His name's Andy Bruno, and he works on environmental contamination from the Soviet Union. So he's a Russian historian, a Soviet Union historian, and basically about the degradation that the Russians have done to Soviet Union did to Russia. So he was having some issues with understanding why this pollution problem was causing such a problem in this area, but not over here. And I says, well, where are they at? And then he told me, and I'm like, oh, because you have crystalline rock there. You don't have anything that absorbs the high pH, the low pH water. And so when you have acid rain, it stays very acidic. But if you have places with like limestone, that's going to change the pH and be more buffered. And so there was no buffering going on in this one location. And so I sat there with the geologic map and went over where his pollution was and why there was differences in these different areas. And it was amazing is that he really needed a geologist to come in there and talk about some of the physical and chemical processes in order to be able to understand how this impacted the humans in these different areas. And so geologist understanding your basic minerals, your faulting and folding, so understanding structural geology, faults and folds impacted, chemical alterations, your geomorphology, all of those things impact where the water's flowing through. And so you have to understand all of those other fields. That's why this is a 600 level class, not a 400 level, because I need you to know all those fields beforehand. So a small percentage of America's usable groundwater supplies are contaminated. So groundwater is one of our biggest things that we, 25% in the United States use groundwater. A lot of places use surface water in the United States. Around the world, it's much higher, but in the United States, it's about 25% of using it. Now, a lot of our groundwater supply is a small percentage of America's usable groundwater supplies are contaminated. And usually that's where there was reasons for chemical activity. So major cities. So like Chicago. Chicago doesn't use the groundwater, okay? They can't. Oh my gosh. We'll get into, if you guys really want to talk about some fun stuff, we can get some of you guys to talk about the salt problem. Some of those shallow groundwater in the Chicagoland area is as salty as ocean water because they put so much salt down on the roads that it's contaminated. The shallow groundwater in Chicago is really bad. But we don't drink it. So do we need to clean it up? And I had that discussion, we had that the other day in class here was, If no one's using the water and it's not impacting the ecology of the area, do we really need to clean it up? And that's a whole other debate we can have. But a lot of our groundwater, because it takes so long for contamination to get into it, that a lot of times our groundwater aquifers are still clean. You can go deeper. Around here, our biggest problems are like nitrates, phosphates inside of our drinking water supplies if we have groundwater. But the groundwater you're drinking, like the tap water here, the well that comes from, one of the wells in town, well number 15, is 1,500 feet deep. The water you're drinking now is, thousands of years old. I mean, you get up to places like Genoa and Kingston, their water is from the last glaciation. That's what you're drinking. So you're drinking water that's very old. So we can actually talk about groundwater mining and everything. So a lot of times it's not as contaminated. But the thing is if it is contaminated, it's going to affect a large number of people. The other thing is if groundwater is contaminated and it's impacting streams, rivers, ecology, we're concerned about that too, not just the humans. And then there's a challenge protecting our uncontaminated groundwater, and this is where it's really important. So a country like Denmark, if you guys don't know this, Denmark their regulations for their country state that they are not allowed to treat your tap water. Okay, no treatment is allowed of tap water. Okay, the only thing they're allowed to do is take the water out of the ground and aerate it. So they put it into these big areas and they aerate the water, because we have this thing where water that's stagnant, because typically when water is stagnant, it meant something bad about the water. So we learned to like bubbles in our water. We also learned evolutionarily to like cold water, because that meant it was coming out of the ground and was probably pure. So we've evolved to like things with bubbles and cold. So that's why we like cold pop. I mean, honestly, it's an evolutionary thing. That's why hot and, we like that taste. So in Denmark, they're not allowed to treat any of their groundwater except for put gas into it, so just bubble it. Well, what does that mean? That means that they protect their groundwater, because the country 100% uses groundwater for their drinking water supply. That means they are obsessed in that country with protecting all their groundwater, knowing exactly what all pollution is, because what they did was they put that as their national priority, never to have to treat water and never have to deal with pollution of their drinking water supplies. So instead of waiting until something is polluted, then having to treat it and find new wells and everything else like that, and try to do all this back end stuff, they just do it in the front end. So I think Denmark's amazing. So when you want to talk about hydrogeologists, Denmark really knows their stuff on contaminant. Thanks. We're going to talk a little bit about laws here. So some of the things I've already mentioned is MCL, maximum contaminant level. And then we also have maximum contaminant goals. So we have goals because we can never get to zero. And that's another misconception that people have, is that when they have their drinking water, they want nothing in it. But in actuality, if you drink distilled water, it's bad for you. And why is distilled water bad for you? Do you know why? You should never drink distilled water. Did you know that? No? Okay. So why should you never drink distilled water? Okay, so you guys remember from chemistry, basic chemistry, osmotic pressure? So what happens if you have a whole bunch of minerals on one side of a membrane and you have none on the other side? It's not stable. And what happens? It wants to form an equilibrium across that membrane, right? So view your stomach cells as that membrane. You have all these salts and minerals inside of your cells, and you're drinking distilled water, which has nothing into it. So what is that doing? Is it sucking all those minerals out of your cells to try to go into equilibrium with it? So distilled water is actually really aggressive and really bad because it wants to be in equilibrium. So it'll take the pipes, it'll try to strip minerals from pipes and everything. It's actually very aggressive. So you can never say water is zero, okay? And it's also impossible to ever have negative or zero, because we never can know for sure. And that's one thing you guys will get into with contaminant. You never report something as zero, okay? Like there's nothing in the water. It's always less than the detection limit of the equipment because it might be in there. But do we really care about parts per quadrillion concentrations of something in there? We need a certain amounts of like copper, okay? If we have no copper in our diet, we will die. we need a little bit of copper. We need a little bit of zinc. Those multivitamins that you guys all take, which I think is ridiculous. You shouldn't take them. If you take a multivitamin, unless your doctor tells you have to do it because you have certain nutrients, multivitamins, you're just mining things out of the ground and then you're just peeing them back into it. Americans have the most expensive urine in the world. Because we mine all of the stuff that we don't need. And if your body doesn't need it, it just comes right back out your urine. And then we have it in our wastewater treatment plants and then it puts it into it. So don't take a multivitamin unless you have to. You have a major deficiency. Oh, we can talk about vitamin D if you guys want to have a discussion about that at some point. There's a lot of women in this class, so we all end up with a vitamin D deficiency. Okay, we can talk about that. But if you just drink a glass of milk, you're fine. But so the goals are where we'd like to be. Maximum contaminant levels are enforceable standards. Okay, so this is where we enforce that, like I said with TCE, that 5 ppb. But we have certain things like arsenic used to be at a really high level, and the Clinton administration changed it from 50 parts per billion down to 10. And then we have an MCL goal of 5, because we actually found out that if any concentrations greater than 5 parts per billion of arsenic actually affects children a lot. It's kind of in that same kind of line as lead. Arsenic, there's no safe levels of those things. Arsenic, we don't need arsenic. In actuality, it's really interesting, too, is a lot of things that we don't need that are actually toxic for us don't dissolve into ocean water. And so when we talk about like evolution of life and stuff, things that are in little minor concentrations in ocean water, we kind of need, and things that never dissolve, we don't actually need. So it's kind of interesting how, the earth and us all combine together. Maximum contaminant level are enforceable. So this is where you get the legal limits of things. Now, not everything has an MCL. We're going to be talking about PFAS later on. PFAS is PFAS, PFAS. It stands for polyfluorinated alkyl substances, Teflon. So if you haven't watched The Devil We Know, watch it and you'll be like, oh my God. Have you watched that yet?
On my list now.
It's on the Blackboard site.
Yeah.
There's a YouTube. It's on YouTube. It's also on Netflix. So.
Yeah, that's why I put it on my list.
Oh, you should watch it. Watch it with friends.
Yeah.
Because you're going to be like, okay. But there's no MCLs for it. So that's one of the problems with MCLs is you can get into government regulations. What's the importance of government regulations? Well, the thing that it does is it forces you to have below a certain level. And if something doesn't have an MCL, unless us as the public say we demand to have less of this in our water, if it's not regulated, there is no enforcing of it. So the polluter, unless there is a financial, you sue them, there's a legal, they'll want to dump. And so when you watch The Devil We Know, and you'll see why we have regulations, why we have to have regulations and enforceable regulations in this country. A lot of other countries around the world I deal with all the time have the same regulations we do, but they're not enforceable, so things get dumped all the time. So we have to have a strong EPA. So thank you, Alyssa, for working for the EPA. So risk in drinking water. So one of the things that you can get from drinking water is cancer risk versus toxicology. We're living through this right now, or what's an acceptable risk? So we try to set risk at 1 additional cancer risk per 1 million people. Okay, so we try to set it to around 1 million people or 100,000, depending on the compound, because what we want to do is say that you're never going to, life causes death. So if you're getting exposed to really low levels of a cancer-causing agent, we don't want it to be more than 1 in 100,000 or 1 in a million people die of cancer. So we try to set that low. We try doing it with rodents. We try to extrapolate down to these really low levels, and a lot of times it just doesn't work. We really don't know from a biological standpoint, because we can't do those experiments on saying, okay, we're going to have 1 million people, we're going to expose you to this amount of a contaminant over 20 years and see if one person gets cancer. So we do a lot of extrapolating from high levels of knowing that, okay, 100 people will get cancer out of 1,000 people at this level. So if we extrapolate down, this is what the levels should be. Or we use rodent or animal models to pick these levels. But sometimes we don't even do that. So our big contaminant problem we have here in DeKalb is radium. It's a radioactive nucleotide, and it's underneath. If you guys look at a periodic table of elements, it's right underneath calcium. So what happens is when you drink radium in, it's the same size, it's the same chemistry as calcium. So we take it into our bodies and it gets into our bones, but it's radioactive. Well, they set the MCL for radium at the detection limit of the equipment. At the time. Now we have better equipment, but at the time, 5 picocuries per liter. So we just set it at the detection limit of the equipment. We don't actually know if that's if you're going to get cancer at 5, 7. We don't actually know any of that. They just pick the MCL at the detection limit of the equipment. So sometimes these MCLs are based upon a lot of toxicology research. We've gone into a lot of it. Some of it's just equipment. Some of it is also legal. Politics get a lot into it. The politics of this is tremendous because people will, and we'll talk about it with the fluoride wars. We'll read a whole book. There's a book called The Fluoride Wars and all about fluoride. So we're going to talk about fluoride in water and why is it set at 4 when that's really a bad level. And we'll talk about fluoride. And then things like chlorine. Chlorine, we know, kills pathogens. I mean, the wipes, the Clorox wipes that are sitting somewhere in the room here, kill viruses and stuff like that. But we put this into our water. We put chlorine into our water because for public health reasons. Well, it's better to kill pathogens and not die of disease all the time than the little bit of a cancer risk you're going to get from chlorine. So which is better? And if chlorine mixes with, so methane here, the word methane means 1 carbon. Halo means for halogens. So that's your far right part of your periodic table of elements. That's the halogens. We'll go more into this in this class. And so it means 3 of those compounds along the blue. So if you guys are looking at the periodic table right over there, it's the blue one. It's, not the far right because those are gases. It's the one right over to it. It's the halogens. So it means it's got 3 halogens onto a carbon. So trichloroethylene is 2 carbons because ethylene, we'll go into that in a second. But halogens, it means it's got 3 of the chlorines hooked to a carbon molecule. Well, this causes cancer. So this is a known carcinogen. And so what happens is if you have organic molecules mixing with chlorine, you'll get this known carcinogen. And this will come back when we start talking about Flint. This is one of the problems that happened in Flint, was they had a lot of trihalomethanes being formed. And those have MCLs. So that causes a little bit of a cancer risk, but what's the risk from this? And so it's always fun. It's one of the things we can never say, well, we want 0, we want this. We have to weigh risks of corporations, of public health, of community health, government so all of these things come into play when we start looking at MCLs, environmental laws. So environmental laws, they started in the 1970s. You guys are going to look at Silent Spring. If you guys haven't read it yet, you'll be surprised. You'll be reading it and you're like, isn't this today? And it's like, no, this was back in the 60s. So we're still dealing with some of the same issues, different contaminants, but similar issues. Because of that book, we started the environmental protection laws. Also, just as a side history note, Nixon the Watergate affairs were starting to happen and he was starting to get into a lot of trouble. And so he thought this was a way to save his political back was by starting all these environmental agencies because all these people were trying to fight for all these environmental things. So he thought it would improve his rankings amongst people. He still got kicked out and everything like that. So, but we got the positives from Nixon is all of these federal laws in the Environmental Protection Agency. And so in there, then we had NEPA, which was the National Environmental Policy Act in the 1970s. It's a federal act. It requires agencies, governments, and industries that propose a major action must know what the environmental impact statement is. So one of the things that we've been having this act that says, well, if you're going to do something, tell us what the effect is to the environment and to humans. So if you're going to dump, like BP, dump into the ocean or dump into Great Lakes, you have to put into an environmental impact. What is the impact from doing this? Well, under current regulations, our current administration is trying to get rid of these, trying to say that, industry knows best. So. But this is really important for us to have this, is to say you have to know what your environmental impact is going to be. And if it has none or there's no humans around, What does it matter? But what happens if it's impacting, say, a salmon? So talking about Alaska, you might want to look into, for some of your papers for this class, is the copper mining that they're planning on doing up in Alaska. What is that one called? It'll come to me. So the Trump administration just passed it so that could go forward with the mining. So what is the effect from a contamination point of view of polluting in Alaska if they're doing mining? Well, there's no people there. Well, there's some indigenous people, but there's salmon. And so what's the effect of some of the mining operations? Or you might want to look into acid mine drainage. We'll talk a lot about that. But if you're going to be working in Alaska, that's another. Well, Alaska's also got oil. So I'm not sure. Where's your site at in Alaska?
It's covering the Brooks. It's like large scale, so it's a Brooks range.
Oh, okay. So yeah, big things. Okay. Yeah. I'm not sure. I can't remember where that copper mine is in Alaska.
Actually, I think I remember reading an article about it recently.
Did you?
It's been in the news. I was going to ask though, does that include like remediation and plans for cleanup, or is it a different city?
So the question was about EIS, if those include remediation. No, these do not include remediation. That's a whole different law. That's coming up. That's the CERCLA and RCRA that are coming up. EIS is just basically says, what would you do if you do what you're planning on doing, not if you're going to clean it up. We don't have, and part of what they'd like to do is put more things into there is if you do cause any damage, how are you planning on cleaning it up at the end? So there is a little bit of that. It doesn't cause remediation. Like, it's more of, if you're going to cause a mining and you're going to be putting this over there, what's your long-term, like, are you going to plan on reseeding it? Are you going to fill the mine up? What are you going to do after you're done with whatever you're doing? So there is parts of that in there. So if that's what you meant, yeah. So yeah, the environmental impact statement does include like what are you going to do at the end? How are you going to close up the site? Now, remediation, and we'll talk a little bit about CERCLA, because what ended up happening is people pollute all the time and then they don't have that in there, or something happens. So, but yeah, you do have to have what are you planning on doing at the end. So it's full disclosure out there. But the government agencies mandate particular results, and it does not require federal agencies to adapt the least environmentally damaging alternative. So one of the things that happens, people think is, and especially what happens when people are fighting these things, whatever large-scale operations you're talking about, when these things get fought, when people are fighting them, is they're like, well, it's causing environmental damage. Well, it doesn't have to do the least environmentally damaging thing. We still have to live on this planet. We still, you guys still want your iPhones. You still want things. So if we're not going back to where we were hunters and gatherers, we're going to have an impact. So it doesn't have to be the least damaging. It just we have to know what the damage is and how are you planning on dealing with it. The Clean Air Act and the Clean Water Act came out in the 70s. The Clean Water Act made fishable and swimmable waters. So WWTP stands for wastewater treatment plants. So what happened is this act here created enough money to build wastewater treatment plants everywhere, because wastewater treatment plants were probably one of the main sources of a lot of our pollution in the waters, was all of the sewage going into all of our lakes and rivers. And you see this around the world. I mean, this is one of my big things I work with, is like they're just dumping their raw sewage in the city of Mandalay into the Irrawaddy River, and they wonder why their dolphins are getting sick. So we created the Clean Water Act to have money to build wastewater treatment plants, and that's probably one of the biggest things that we've done is develop wastewater treatment plants. I mean, it is a misconception with a lot of students. A lot of times they think that we should go back to the good old days, like it was cleaner in the 60s in the United States. Oh, the 70s? Oh, no. Air was horrible. I remember even in the 80s, we went out to Las Vegas to visit my uncle, and I couldn't breathe because of how bad the air pollution was. My eyes were sealing shut. I was actually, because I never had experienced that much air pollution problems. Now you go to Vegas and there's no problem. It's because we put in these laws and regulations. The United States is actually better off, but we can't go back to where we were. And that's the part of the problem, is people don't see a problem now. So they're like, well, let's pollute again. CERCLA came around. I'm just going to continue on. I only have a few more slides here because I don't want to go on into the next day and work on this. CERCLA is the Comprehensive Environmental Response and Compensation Liability Act, and this is what started Superfund. You can see it's not Superfund and Superfund. Started in the 80s. This was where we basically we put a tax on hazardous substances and on chemicals. And so what we did was we taxed them to put this money into a fund in the 80s to clean up sites that were abandoned or the people went out of business. Because a lot of times when people will do the pollution, even though they may have had their, well, I plan on doing this, they went out of business, they walked away from a site, they can't find out who legally owns the ground, because whoever owns it today is responsible for cleaning it up. It doesn't matter who did the pollution. The way this law is written is you own the land, you clean it up, okay? But you can sue other people who did the pollution to try to get the money to pay for your cleanup. But you are legally responsible for your whatever you own today. Doesn't matter who did it, which really makes it much better because then we know if you want to buy a site. So like Walgreens has a really large environmental subsidiary part of their company because they like buying old gas station corners, which have pollution into them. And so they hire a lot of contaminant hydrogeologists to clean up sites and to keep their sites clean because they want these really busy corners that used to be gas stations. So, but they're responsible for it. They can't sue the mom and pop gas station that used to be there. So that's a great thing. The Superfund amended sites, you can clean up the sites. There's on-site treatment. You have to look at what's cost effective. Again, if it's not impacting anything, maybe you just let it sit. If no one's going to be getting into the ground, it's not leaking out anywhere, just maybe letting it sit. So you have to think about all those different things. And then you come up with a plan of attack. If you really are interested in the law stuff, this is about as deep as I go with the law stuff. If you really are interested in it, there is a class over in the law school she teaches every year on environmental law where she goes into all of the regulations and laws and everything. I just kind of mention the titles of things because if you're going to get a job, you're going to be dealing with these things. But in this class, I don't really spend that much time on the laws and regulations. Okay, that is all I have for today. So I'm going to stop my